Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is the second major exam of Math 223, Term 232. Let us have a look to the exam and solve it together. The first question, W, is defined to be all polynomials of this form, where A is a real number. Determine whether W is a subspace of P2 or not. Well, P2 is a vector space consists of all the polynomials of degree less than or equal to 2. So to prove that W is a subspace of P2, we need to show that W is closed under addition and under scalar multiplication, which means that if we take any two vectors in W, their sum should be in W. And if we multiply any vector in W by any scalar, and scalar means any real number, then the product will be also in W. Well, we need to understand the definition of W first. It consists of all polynomials of this form. Well, what is this form? This is a polynomial of degree 2. This is the term with x squared, and this is the term with x, and this is the constant term. So the constant term is always 2. If the constant term is not 2, then the polynomial is not in W. And the second thing, the coefficient of x is negative a, and the coefficient of x squared is a. So any polynomial satisfies these conditions, it would be in W. So for example, P1, 2 minus 3x plus 3x squared belongs to W. This is in W. But 1 minus 3x plus 3x squared is not in W. For example, 1 minus 4x plus 4x squared is not in W because the constant term is not 2. And minus 2x plus x squared is not in W because the coefficient of x is negative 2, while the coefficient of x squared is 1. So we understand now the definition of W, the polynomials inside W. So you think, are these polynomials closed under addition? If we add two polynomials in W, their sum would be in W? And the answer is no, because when you add two polynomials in W, you will add the constant terms, and then you will get 2 plus 2, which is 4. So it will not be in W. Also, multiplying by a constant, by a scalar, will not make it in W. So you can prove this fact that you understand now that W is not a subspace of P2. You can prove it in 3 different ways, if you like. Okay. So you can say let P1 equals to this, and it is in W, and let K equals 3, for example, then 3P1 would be equal to 6 minus 9x plus 9x squared. And this polynomial is not in W. And you can tell him why. Constant term is not 2 because the constant term should be 2. So W is not a subspace. Is not a subspace of P2 because it's not closed under scalar multiplication. Okay, because it is not closed under scalar multiplication. Or you can take two polynomials in W and prove that their sum is not in W because the same, because it's not closed under addition in that case, and the constant term will not be 2. So you can say that let P1 be 2 minus 3x plus 3x squared and P2 2 minus 4x plus 4x squared. Then P1 and P2 belongs to W, but P1 plus P2 would be 4 minus 3 minus 4 minus 7 plus 7, and does not belong to W because constant term is not 2. Then W is not a subspace. Is not a subspace of P2 because it's not closed under addition. Or a third way to prove that it's not a subspace. 0 element in P2, which is 0 plus 0 times x plus 0 times x squared. This is the 0 in P2. P2 consists of all polynomials of degree less than or equal to 2. And this is the 0 polynomial in P2. And this 0 polynomial does not belong to W since the constant term is not 2, it is 0. So W is not a subspace. If the 0 polynomial or if the 0 element in the vector space does not belong to the set W, then W is not a subspace. All of these three uh, different proofs are possible and all of them are correct. Let S be consists of these three polynomials where P1, P2, P3 show that S is a basis of P2. Same P2 set of all polynomials of degree less than or equal to 2. Now we know that dimension of P2 is 3. The dimension of P2 is 3. And there are 3 vectors in S. So equals to the dimension. And in this case, to show that S is a basis, it is enough to show that S is linearly independent. To prove that S is a basis, you need to show that S is linearly independent and it spans P2. But if the number of vectors in S is equal to the dimension, one of these two would be enough, proving that it's linearly independent or proving that it spans P2. But proving that linearly independent is easier. So let us show that the three vectors in S are linearly independent. So how to prove that linearly independent? We have K1 times P1 plus K2 times P2 plus K3 times P3 equals to 0. And then we have to show that there is only one solution of this system, which is the trivial solution. K1 equals K2 equals K3 equals 0. So now this equation will give me a system. Let us write K1 times P1. What is P1? It is 1 plus x squared. And P2 is x plus x squared. And P3 is x squared equals to 0. Now, here, polynomials, you are dealing with polynomials. So the constant terms should be equal to 0 because the right-hand side is 0. 1 times K1 plus, there is no constant term here. There is no constant term here. So K1 should be equal to 0. Now, what about the coefficient of x? Coefficients, the sum of all coefficients of x should be also equal to 0. So K1 times x, K1, K2 times x, so plus K2. These are the coefficients of x. There is no x here. This should be also 0. And now coefficients of x squared should be also 0. So K1 times x squared, K2 times x squared, and K3 times x squared. So this is the system. It's clear that K1 is 0. So from here I'll have K2 is 0. And from here I'll have K3 is 0. So K1 equals K2 equals K3 equals to 0. So S is linearly independent, then S is a basis of or for P2. Now, this is one way also to prove. You can prove this in many ways because this is a system. You can find the solution of the system using Gauss and Jordan elimination. You can find the solution of the system using AX equals B, and then X would be A inverse times B. This system was easy, and I just wrote the system and I found that the solution is there, so I did it like this. This is part one. Part two, express this polynomial as a linear combination of vectors in S. Then find the coordinate vector of P relative to S. So let us write P, which is 7 minus X plus 2X squared as a linear combination of P1 plus and P2 and P3. Again, this is a system, but we will not have the right-hand side zeros in this case. We will have K1 equals 7 and K1 plus K2 equals the coefficient of X, which is -1, and K1 plus K2 plus K3 equals the coefficient of X squared, which is 2. K1 is 7, so 7 plus K2 is -1, so K2 is -8. K1 is 7, K2 is -8, 7 minus 8 is -1. Take it to the other side. So K1 is 7, K2 is -8, K3 is 3. So P would be equal to 7 P1 minus 8 P2 plus 3 P3. And the coordinate vector of P relative to S, we denote this by PS. This is the coordinate vector. You write only the coefficients 7, -8, and 3. Notice also that this system was easy to solve like this. But if the system is not easy to solve, then I will use Gaussian elimination or AX equals B, any method you can use to solve the system. And if the calculator is allowed, you can also use the calculator. Find a basis for the solution space of the homogeneous linear system and find its dimension. So let us solve the system first. Let me write the augmented matrix. Let us use Gaussian elimination and Gaussian Jordan. So this is one, I'll make 2, 0. -2 plus 2 is 0. 8 minus 8 is 0. -6 plus 6 is 0. 2 minus 2 is 0. So I have one equation, which is the first equation. There are 4 variables in this question. Only the first one is basic. The other 3 are free variables because we don't have leading one here. So to solve this system, I call x2, for example, t1, x3, t2 parameters, and x4, t3. And then x1 would be take everything to the right-hand side. For x2, that's 4t1, minus 3x3, that's t2, plus x4 or plus t3, and all of these parameters could be any real numbers. Now this is the solution of the system. He needs a basis for the solution space. There is a theorem that says the solution, if it is infinitely many solutions like this of a homogeneous system, it's the subspace. So we call it solution space. How to find bases? We write, we have x1, the points. We are in R4 here because there are 4 variables. We have x1, x2, x3, and x4. And x1 is 4t1 minus 3t2 plus t3. And x2 is t1, x3 is t2, x4 is t3. And now we take t1 as a common factor or not a common factor. And we take t1 and write the coefficients of t1 here, the point where all coefficients. For example, in the first coordinate, we have 4t1, so we write 4, the coefficient of t1 in the first coordinate. In the second coordinate, there is a t1 and the coefficient of t1 is 1. There is no t1 in the third or the fourth coordinate, so we can write it like this. Plus, now t2, do the same. So in the first coordinate, I have negative 3 t2. Second coordinate, no t2. Third coordinate, I have t2 with coefficient 1 and here 0. Do the same for t3. I have coefficient 1, 0, 0, and 1. By writing this vector in this way, we find the bases because you can see here that any point in the solution space is written in this form, which is this form. So we can write it as a linear combination of these three vectors. So any point in the solution space can be written as a linear combination of these three vectors. This means that these three vectors span the solution space. So they are the required bases. So S or the basis is 4, 1, 0, 0, negative 3, 0, 1, 0, and 1, 0, 0, 1. This is a basis for the solution space. So any solution of this equation, of this system, sorry, can be written as a linear combination of these three vectors. So they span all the solution space and they are a basis. What would be the dimension? We have three bases, three vectors in the basis. The dimension is always the number of vectors in the basis. So it is equal to 3. The dimension is 3. S, standard basis for R2. B, basis, another basis for R2. Find the following, the transition matrix from B to S. To find the transition matrix from B to S, we write S, the new base S. We need to transform from B to S. So we write S first here. S consists of 1, 0. 1, 0, we write it as a column. 0, 1 is another column. So this is the basis S. Then we write vertical bar and we write B. B consists of B1, we write it as a column. B2, we write it as another column. And we work with this matrix. We change this matrix in the left to the identity matrix. When we change it to the identity, this would be the transition matrix. But this is already the identity matrix. So here, the transition matrix from B to S is equal to 2, negative 3, 1, and 4. Because S is the standard basis. So if S is the standard basis, then the transition matrix from any base to S is the base itself, B. Now, find the transition matrix from S to B. Well, here you have two methods to find the transition matrix from S to B. You can work like here, but you need to write B first, and then you write S, and now you need to work with this matrix and change it to the identity. So I will interchange row 1 and row 2 to have 1 here, and then use the 1 to make 2 0, negative 2 R1 plus R2, negative 2 plus 2 is 0, negative 8 and minus 3, negative 11, negative 2. And now negative 11, I need it to be 0, so I divide row 2 by negative 11. Two over 11. And now I need the 4 to be 0, so negative 4R2 plus R1. Now 4 over 11 plus 0, negative 8 over 11 plus 11 over 11. So the transition matrix from S to B is equal to 4 over 11, 3 over 11, negative 1 over 11, and 2 over 11. So this is one way, or there is a fact we know that these two transition matrices are inverses of each other. So the transition matrix from S to B could be found by finding the inverse of the transition matrix from B to S. And we know how to find the inverse of matrix. 1 over the determinant, 2 times 4, 8, plus 3, that's 11, because minus minus 3. 2 and 4, we change positions. Negative 3 and 1, we change signs, but we keep positions. And this is exactly this matrix. 4 over 11, 3 over 11, negative 1 over 11, and 2 over 11. Now, part 3, this is W, a vector. Find WB means what? The coordinate vector of W relative to the basis B. So 5 and negative 3, which is B, we need to write it as a linear combination of from the elements of B, 2, 1, and negative 3, 4. So I will write it K1 times 2, 1 plus K2 times negative 3, 4. And we solve this system and find the values of K1 and K2. I'll have two equations, 2K1 minus 3K2 equals 5, and K1 plus 4K2 equals negative 3. This is a system. Solve the system by any method you like. For example, I will solve it by elimination. I will multiply the second equation by negative 2. So negative 2K1, negative 8 K2 equals 6. Add negative 11, K2 equals 11. So K2 is negative 1. Put it in the first or the second. I'll put it in the second. K1 plus 4 times K2, so minus 4 equals negative 3. So K1 is negative 3 plus 4, that's 1. So 5 and negative 3 is equal to K1, which is 1, minus negative 3 and 4. So I wrote 5 and negative 3 as a linear combination. Then WB, then 5 or WK, B, the coordinate vector is equal to 1 and negative 1, K1 and K2. This is WB. Then find WS using the transition matrix. Well, there is a formula that says to find WS, of course, W is a vector, okay? And you have WB, you need to multiply WB by the transition matrix that takes you have B and you need S, from B to S. You have B and you need to go to S. So you multiply WB by the transition matrix from B to S. And the transition matrix from B to S was this one, 2, 1, negative 3, 4. Multiply by WB, then WS would be 2 plus 3, 1 minus 4. And you will notice that WS is W itself. Can you tell why? Because S is the standard basis for R2. So if you want to write 5 and negative 3 as a linear combination of E1 and E2, it would be 5E1 minus 3E2. So WS would be 5 and negative 3. And this proves that my solution is correct because WS should be equal to 5 and negative 3. The last question, A is a matrix. This is 0. So it's a lower triangular matrix. And if the matrix is lower triangular or upper triangular, then the eigenvalues are clear. They are the numbers on the main diagonal. So you don't have to use this one, lambda I minus A, the determinant equals to 0, because if you use it, you will get 6 and negative 1. Now to find the eigenvectors and the bases for each eigenspace, let us deal with 6 first, lambda equals to 6. We need to solve the equation lambda I minus A matrix times vector x equals to the vector 0. So what is lambda I minus A? It is lambda. Let me explain it to you in case you don't know it. I is the matrix 1, 0, 0, 1. So lambda I would be lambda 0, 0, lambda. Now subtract lambda I minus A. So you will get lambda minus 6, minus 0, minus 1, minus A, and lambda minus minus 1. So this would be lambda I minus A. I need it as a matrix. Multiply it by x, let us say x and y, the variables, equals the 0 matrix, 0, 0. But lambda here is 6. So I have 6 minus 6, that's 0, 0, minus 1. 6 plus 1 is 7. Now, to solve this system, I need to solve this augmented matrix using Gauss and Jordan. So interchange row 1 and row 2 and multiply row 2 by negative 1. So this would be the solution. I have x minus 7y equals to 0 and 0 equals to 0. X is a basic variable and y is a free variable. So x is 7y, which I'm going to call t, and y is t. And t is any real number. So this is the solution of the system. If I want to find bases, I write it xy. X is 7t, y is t. I take t. So I can write any element in the solution as a linear combination or as a multiple of 7, 1. So the basis consists of this vector, which is 7, 1. And the dimension is 1 because there is one vector in the basis. And this is the eigenvector. The eigenvector is 7 and 1. Okay. Now, if lambda is negative 1, then I'll have negative 1 minus 6, 0, negative 1 plus 1, and 0, 0. Let me interchange row 1 and row 2 and multiply row 2 by negative 1. 7 row 2 plus 7 row 1 plus row 2 will give me this matrix. This is a final form. X is basic, Y is free. I have X equals to 0. This is XY, coefficient of X, coefficient of Y. So 1 times X, 0 times Y equals 0. So X equals to 0. And Y is a free variable. So Y is T. And T belongs to R. So X, Y would be 0 and T, taking T outside. So the basis here consists of one vector, which is 0, 1. Every other vector is written as a multiple of 0, 1. And the dimension is 1 of the solution of the eigenspace, which is the solution space. Part 3, find the matrix B that diagonalizes A. You should know how to find P. You write the basis, the first basis as a column, and the second basis as the second column. So this would be the matrix B. Show that B inverse AB is a diagonal matrix. This is the meaning of P diagonalizes A. It means that P inverse AP is equal to D, where D is a diagonal matrix. So B inverse AP would be B inverse, I need the inverse of this matrix, 1 over 7 minus 0. 1 and 7, I change positions. 0, 1, I change their signs. Times A, which is 6, 0, 1 minus 1. Times P, which is 7, 1, 0, 1. I need to multiply these matrices. So 1 times 6 plus 0. 1 times 0 plus 0. Negative 6 plus 7. 0 minus 7. Now multiply 42 plus 0. 6 times 0 plus 0 times 1. 7 minus 7. 0 minus 7. 42 over 7 is 6. 0, 0, and negative 1. So this is the matrix D, and we know, you should know that the answer should be like this. And since I wrote 7, 1 here in B, so you should see 6 here, because 7, 1 is the eigenvector corresponding to 6, and 0, 1 corresponds to negative 1. So 0, 1, I'll have negative 1 here. If you write P as 0, 1, 7, 1, you will have negative 1 and 6 here. That's the answer, and I hope you enjoyed solving this exam with me.